Okay, so the second part of today's lesson is also about proving triangles by SAS. And so if I have two triangles over here, right, A, B, C, and D, E, F, one way to prove it is, of course, using side, side, side. If the corresponding sides are all proportional, we can say that the two triangles are similar by side, side, side. So what's SAS? Well, it kind of means what it sounds like. If I have these two triangles and I tell you that let's say angle B is congruent to angle E. Okay, if angle B is congruent to angle E, and AB corresponds to DE, and BC, which corresponds to EF, right, if they are proportional, then what I can say is that triangle ABC is similar to DEF by side angle side. Okay, so SAS. And this angle right here, right, the angle that's between the two sides that are proportional, right, this angle is between this side and this side. This angle is between this side and this side. And these are the two sides that correspond or are proportional to each other. It's called the included angle, okay? So I think you may have heard that term before in the past in the context of proving congruent triangles, right? You can also prove two triangles are congruent by side angle side, right? But instead of saying that these two sides are congruent, right? AB is congruent to DE, BC is congruent to EF. We now say that these two sides, this side and this side, are proportional, okay? So SAS is a way to prove that triangles are congruent, but it's also a way to prove that triangles are similar with the caveat that the two sides between the two that make up this included angle, I should say, are proportional instead of congruent. All right, so I only have one example over here. If we take a look, show that the triangles are similar. Triangle SRT is similar to PNQ. And SRT and PNQ looks like they're already lined up for you, right? How do I know SRT? Letters go from top to bottom to the right, top to bottom to the right. They all line up. So, well, it kind of looks like we are going to be using our SAS theorem here, right? Because they don't give us the third side length. And later on, when we go on to chapter 9, we will go over Pythagorean theorem. So let's see if SR, the ratio of SR is to PN is equal to the ratio of RT is to NQ. Okay, so let's check that first. 24 is to 18, question mark. RT is to 21. RT is to NQ, I should say. 28 is to 21. And it looks like if you divide top and bottom by 6 over here, you're going to get 4 over 3. And over here, if I divide top and bottom by 7, you are also going to get 4 over 3. Okay, so the corresponding sides, this side and this side, this side and this side, look like they're proportional, right? And the included angle, right, angle R and angle N, well, those are right angles, right? And we call this the right angle theorem. We'll call it RAT, RAT. Okay, all right angles are congruent. Then these two triangles are similar. I'm just going to repeat that statement. Triangle SRT is similar to triangle PNQ. Oops, PNQ, the ordering of the letters matter, by side angle side. Okay, so I just need to establish that these two sides and these two sides are proportional. And I have to mention that, hey, these two angles, the included angles between those two proportional sides is congruent. Okay, so all right angles are congruent. Okay, so very last example right here I have is triangle XZW is similar to triangle YZX. How do I show that? Now notice these two triangles are, actually there should be a right angle over here, are not quite drawn up. They're not quite lined up. And so if they're not lined up, if you can't quite visualize it in your head, I would just draw a picture, okay? And they even give you a similarity statement, right? They said YZX. So if YZX is written like this, why don't I draw my triangle YZX as XZY with this XZ here on the bottom. And so what I mean by that is this. Here's X, here's Z. And of course, this will be W. Okay, so make sure you label WX as 20, ZX is 12, WZ, of course, is 16, right? And of course, I still have my YZX. I'm just going to copy it down one more time. YZX. Okay, so if this is 90 degrees right here, right? This is 90, right? If this is 90, this is 90, right? Because the straight line is 90. And what I find is when you have the two triangles lined up next to each other, it's kind of easier to see which side corresponds to which. Of course, you can go back and label, hey, this is longest, middle length, shortest, right? Longest, middle length, shortest length. You can line it up that way as well if you don't want to redraw the picture, okay? All right, so now that I've redrawn the picture, right, this problem is almost just like this problem, right? And in fact, on this one right here, you could use a couple of theorems, right? You could use side, side, side to show that, hey, the ratio of WZ is to XZ is equal to the ratio of WX as to XY is equal to the ratio of ZX is to ZY, right, by side, side, side. Or you can use side angle side, right? Personally, I think side angle side is a little bit faster, so it's just one less ratio for me to calculate. So I could say angle Z is congruent to angle Z. And actually, because this diagram right here, right, notice there's multiple lines, I need to be a little bit more specific about what my angle Z is. So actually, I'm going to rewrite this as angle WZX is congruent to angle XZY. Okay, so it's always better to be exact. Clearly, in this picture, right, this is angle Z, this is angle Z. But if we're referring back to the original diagram, when you say angle Z, no one knows what you're talking about. So make sure you be a little more specific. Angle WZX and angle XZY are congruent. You could write abbreviation, right angle theorem, RAT. And of course, you can just say, hey, is 16 is to 12? In other words, is WZ is to XZ, question mark, as ZX is to ZY. Okay, so set those ratios. WZ is to XZ, which is 16 is to 12. And of course, ZX is to XY is 12 is to 9. And you can reduce this, right? Divide top and bottom by 4. You're going to get 4 over 3. And divide top and bottom by 3. You're also going to get 4 over 3. And they are proportional. Okay, so now you can conclude with this statement. Triangle XZW is similar to angle YZX by side angle side. Okay, so again, if you use side, side, side on this problem, it would have worked as well, right? Because they give you all three side lengths. But personally, I find using that included angle right there is a little bit easier. It's one less ratio for me to calculate, right? If I say, hey, you know, if I had shown that WX is to XY, which is also equal to, 4 over 3, and I could have stated that, hey, these two triangles are similar by side, 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 that would have worked as well.